Hi everyone, welcome back to Math 112. This is Scott. Let's get started. So, what we're going to be talking about today will be three sections that are all based on variations of the same couple of formulas. And so in 6.5, we will start with the main formulas that will be the source for all of the rest. And these are formulas, some of which are kind of simple, others of which are relatively complicated, that we will mostly just be learning how to use. So sum and difference formulas. So these will be the foundation for all of the other formulas that we're about to come up with. Alright, so the basic idea here for sections 6.5 through 6.7. There are a wide variety of formulas that we can use, and they are all based on relatively simple ones, and they will be used to find the trig functions of new values based on known trig functions of old values. So we are going to use the various formulas to find the trig functions values at new angles based on known angles. And the way we will do this is you just have to find the proper values of alpha and beta. So the key find the best values for alpha and beta for each situation. And a tip here is that it will be frequently easier if we switch to degrees rather than radians. So a tip. It's often easier if we work in degrees rather than radians. Okay, so this is overarching general strategy, and now let's see what the formulas are so that we can actually put them to use. Now, I'm not going to really prove any of the formulas that we're going to be covering in these sections. I may say how some of them relate to each other, but the reason why I'm not going to prove any of them is because the best ways, the most elegant ways of proving them involve techniques that we're going to learn a little bit later. In particular, in chapter 8, you'll get the best ways of proving any of these. So I'm not going to prove them. We're just going to use them, and trust me, that's going to be hard enough. Okay. So let's start with the sum. The sum formulas. All right, so two basic formulas here that are the source, as I say, of all the rest of the formulas that we're going to learn in this entire section, and the two that follow are about to be unveiled. So, some formulas. Cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And then sine alpha plus beta is sine alpha sine beta, cosine beta. Sine alpha cosine beta plus cosine alpha sine beta. And the way we'll write this is we'll just always, when there are terms that have both sines or both alphas and betas, we'll just always put the factor that has the alpha before the factor that has the beta. And then the tangent formula. So these two, as I said, are the key to all the rest. So the tangent comes from basically just taking the sine formula, dividing it by the cosine formula, and then simplifying a little bit. So it's tangent of alpha plus beta. So take this formula, put it on top of that formula, divide by all the cosines, and what you'll get is tangent alpha plus tangent beta, all divided by 1 minus tangent alpha tangent beta. And again, if you want to know how that comes from these, divide the sine formula by the cosine formula, and then if you divide everything through by cosine alpha and cosine beta, you would get this. Now, the difference formulas, let's just put them all into play so that we can see how we're going to need to use these. So the difference formulas. So cosine alpha minus beta equals. So essentially, the way this relates to the sum formula is, just think about what would happen if beta was switched to negative beta. Well, each of the functions here is either even or odd, and so what that means is the negative either disappears or can be pulled out to the front of the term. And first off, when we're talking about cosine here, we look at it, cosine alpha minus beta is going to be cosine alpha, and then it's cosine beta, which cosine is even, so that means that the negative will just disappear. So this term is unchanged. But then the next term here, sine alpha sine beta. Sine, unlike cosine, is an odd function, so when you switch the beta to a negative, that negative can trickle all the way out to the very front, and so we have a plus sine alpha sine beta. And by the same token, we can figure out what's going to happen with the sine. So sine alpha minus beta. So again, just think about what happens if beta becomes negative. So the first term, unchanged, because it involves cosine beta, which is going to, because it's even, it's just going to swallow the negative and not even notice. Here on the second term, though, the beta is in a sign, which is odd, and therefore the negative will come all the way out to the front. So we've got now sine alpha cosine beta minus cosine alpha sine beta, and then finally the tangent of alpha minus beta And remember, tangent is odd. So all the ones that involve the beta will become the opposite. So it's going to be tan alpha minus now tangent of beta. And on the bottom, it's going to be 1 plus tangent alpha tangent beta. And if there's one thing that writing all these formulas will get you, it's practice writing alphas and betas. The difference between an alpha and an A is it looks a little bit more like a fish. The difference between a beta and a B is that beta actually in some ways kind of resembles the German letter Esset. Okay, now to use these, we have to just break down the angle that we're given into two known angles. To use these. Break the angle given into two known angles. And if we happen to be confronted with a function that is not one of these three, it will be the reciprocal of one of these three. And so we can just figure out the answer for its reciprocal, and then in turn reciprocate that. So if we want to use them for cosecant, secant, or cotangent, first use a known formula. Then take the reciprocal. Okay, let's try this out. So examples. Evaluate and simplify. So one note about this, I would, if I were you, I would commit the sine and cosine addition formulas at least to memory. I would not commit anything else to memory. And instead of committing these things to memory, if you look on D2L under the Content tab, you will find an item called Trigonometric Identities. And what that item is this document right here, which contains an encyclopedic list of all sorts of useful trigonometric formulas and identities that we'll be using in this class. And this particular sheet will be fair game for any exams, quizzes, or anything. You can use this instead of trying to commit all of these various formulas that we're about to be unveiling into your memory. So right here, what we have on the very first two boxes are the sum identities and difference identities, as we just wrote them now. So you can use this as a substitute for having to memorize all of these different formulas. Again, though, I would advise, particularly those of you who are going on into calculus, I would advise you to commit at least the sine and cosine addition formulas. So the sum formulas for sine and cosine to memory. They come up pretty frequently and they're pretty useful. The rest, though, if you can remember how they are derived from those, that's good enough. Okay, so first off here, let's just see how we get this started. So sine of 105 degrees. So this is already in degrees, and so we just need to figure out what two angles do we know that add up or subtract to make 105. And 105, we know that that is, for example, 60 degrees plus 45 degrees. So we'll make this one alpha, this one beta, and we can then just get to work. So then what that means is sine of 105 degrees is the same as sine of 60 degrees plus 45 degrees. And so what we see here is clearly an addition. And so you look at the sum identity, and you see it's sine cosine plus cosine sine. And that, by the way, is how I would remember these. I would remember that the sine sum formula is sine cosine plus cosine sine. So, okay, so this is sine cosine, so it's going to be sine 60 degrees, cosine 45 degrees, plus cosine sine. So cosine 60, sine 45, and then you just think about your unit circle know-how and you remember sine of 60 degrees. So 60 degrees is the high one, so that means the sine being the y will be the big value, root 3 over 2. Cosine 45 is root 2 over 2, plus, and then here cosine 60 is 1/2, and sine 45 is root 2 over 2. And if we want to simplify these, what we'll do is we will multiply together the terms, and when we have square root times square root, those square roots do combine. It's going to be square root of 6 over 4 plus 1 times root 2 is just going to be root 2 also over 4, so we can just write them together as one big fraction. So this is the most simplified form we can get here. We'll see when things get a little bit more involved, we can sometimes have some more avenues for simplification. Okay, so that's how that goes. You take two known angles and you figure out how the angle that you're being given is secretly a combination of those. Okay, let's try one with tangent. The tangent one is the most complicated one as far as the simplification goes for these, and the reason is, well, you're about to see. So a tangent of 195. So again, degrees. Degrees are easier to work with because it's easier to see how the known angles that we frequently work with relate to 2 degrees. So let's think about this. 95 degrees, there are different ways you can make it, but one way might be you think about known angles, and 135 is a known angle, plus 60 would make this. Another possibility would be 150, which is known, plus 45. So that's nice. So you can just, whatever one you come up with first is fine. So I'm going to say the first one I came up with was 120 plus, sorry, I didn't, no, that's not it. Sorry, what did I come up with? I came up with 135 degrees plus 60 degrees. And again, those are both known. That's that one, and that's that one. Okay, so this will be our alpha, this will be our beta, and so what we've got is tangent of 135 plus 60 is equal to, and then you just consult your handy dandy formula, and that will be tangent of 135 plus tangent of 60 degrees, and that'll be the numerator, divided by 1 minus tangent 135 times the tangent of 60, Now 60 degrees, that's the higher one, which means it's steeper, which means the tangent is root 3. 135, that's the 45 degree angle, but in quadrant 2, so that means the tangent will be negative 1 plus root 3 divided by 1, and then in the denominator here, we've got minus negative 1 times, and the tangent of 60 once again was root 3. And so what we have here is negative 1 plus, plus root 3 divided by 1 plus root 3. And if we want to simplify this, we can do it by multiplying by the reciprocal, or I mean by the conjugate of the denominator. Just multiply by conjugate. That's the name for what we're doing here. And it will produce a more simplified version of the answer. So okay, so if we multiply this out, we would have to distribute everything with everything. Negative 1 times negative 1 is negative 1. Negative 1 times root 3, negative root 3 is positive root 3. Negative 1, root 3 times 1 is root 3. And root 3 times negative root 3 is going to be negative, and it's just going to be 3. The square roots will cancel each other, or you can think of it as being the square root of 9. Down in the denominator, we have 1 times 1, negative root 3, positive root 3, and then minus 3. So the reason for doing this is, look how simplified it's about to get. So we're going to have on the top negative 4 plus 2 root 3, all divided by negative 2. And so we can divide everything in on the top by the negative 2 to get 2 minus root 3. So this is the most simplified version of this answer, and that will be preferable. Okay, now let's try one that involves radians, let's say. So how about we try the cosine of 7 pi over 12. Alright, so we got a cosine now, and it's 7 pi over 12. Now 7 pi over 12, the easiest thing here, frankly, is turn it into degrees. And so this is going to be, remember how you do that, you just take the fraction and you multiply it by the corresponding fraction that involves 180 and pi, and you want to cancel the radians and leave behind the degrees. And there we have that, and it turns out 12 goes into 180. And in fact it goes in 15 times, so we have 7 times 15, which is 105. Which we've already analyzed to be 60 and 45. Okay, so we've got our two characters here. So alpha will be 60 degrees, beta will be 45 degrees. And now remember cosine. So cosine addition formula is cosine cosine minus sine sine. And that again would be the way I would remember these. I would say sine is sine cosine plus cosine sine. And for the cosine addition formula, I'd think cosine is cosine cosine minus sine sine. So cosine 60 degrees, cosine 45 degrees, minus sine 60 degrees, sine 45 degrees. Alright, and now what's this going to equal? So cosine of 60, as we already remembered, was equal, actually I guess we didn't write it down, that one was a half, yeah I guess we did, and then root 2 over 2 minus here, and now we're going to have sine 60, which is root 3 over 2, and cosine of 45, which is root 2 over 2. Okay, and then by the same token as before, we're going to have a denominator here of 4, and we're going to have root 2 minus root 6 for the total top. So just like before. Alright, and now let's try one that's going to require us to use one of the difference formulas. So let's say D. Let's say we want sine of pi over 12. So once again, it's easiest if I just think of this as degrees. And I already noted that 12 goes into 180 15 times. Or alternately, I could think, well, this would be half of pi over 6. Now, this is a little bit trickier because I have to think of what minus what makes 15 that among my known angles. And here, once again, 60 and 45 are good places to start. 60 minus 45. So this one was 60 plus 45. This one would be 60 degrees minus 45 degrees. So then, what we're really talking about here is sine of 60 minus 45, which according to the sine difference formula, so that's the subtraction formula, is sine 60 cosine 45 minus now cosine 60 sine 45. And we get, once again, a very similar result to what we've had before. So this is going to be sine of 60 is root 3 over 2, cosine of 45 is root 2 over 2, minus the cosine of 60 is 1/2, and the sine of 45 is root 2 over 2. So what do we have here? It's going to be root 6, root 2, and once again, this is all going to be over 4. It's a very similar results to what we've had before. Nothing too surprising here. All right, well, how about something like this? So the secant, let's go with that. The secant of negative pi over 12. So you notice there's going to be a lot of pi over 12s going on in this particular section anyway, and that's because out of the ones that we do know, this is the easiest one to these are the easiest combinations to produce that make ones we don't know. Okay, so first off, real question here is cosine of negative pi over 12. And we'll first figure that out, and then we will proceed from there. Okay, so cosine of negative pi over 12, that's equal to, now let's think about this. Okay, well, first off, negative 15 degrees for the reasons that we've already seen. And if we think about this, we can just take our old friends 45 and 60, change the order around, so it's 45 degrees minus 60 degrees. And that will get us there. Which in turn, if we use the cosine subtraction formula, is going to be cosine cosine plus sine sine. cosine cosine plus sine sine. Ordinarily it would have been minus, but because it's a subtraction, it becomes a plus. And now let's think about where that takes us. That takes us to root 2 over 2. Cosine of 60 is a half plus 45 degrees, which is root 2 over 2, and sine of 60, which is root 3 over 2. So if this problem had said cosine instead of secant, we would be just about done here. We'd say root 2 plus root 6 all divided by 4. So that's equal to the cosine. But the original problem didn't ask for the cosine, it asked for the secant, so we're not done yet. So, secant of negative pi over 2 then is going to equal the reciprocal of this. Now, the previous version was as simplified as can be because it had all of its square roots in the numerator. This one, however, has square roots in the denominator, meaning it has an irrational denominator, meaning that we have a responsibility to rationalize it. So we will rationalize. By multiplying by the conjugate. So that's what we are typically going to have to do here. We don't want to have infinite decimals in our denominators here. So what we're going to have is root 2 minus instead of plus root 6. Alright, now let's see why. Let's see why this works. So the best reason to see, the best way to see why these types of things work is just to see them in action. So first on the top, nothing much happening up there. Just 4 times root 2 minus root 6. The best I'm going to be able to do is maybe distribute that 4, but we'll see if that even turns out to be useful. And then here, root 2 times root 2, that's actually going to just be root 4, which is 2. The middle terms will be negative and positive of the same thing, so they will cancel each other. And then the final terms will be root 6 times negative root 6, which will be negative 6, which will just equal 4 root 2 minus root 6 all divided by negative 4, which will cancel. All we're going to have left is the negative, which means that we can just change the positive term to a negative term and the negative term to a positive term. And so that just switches the order of the two terms there. And we're going to have root 6 minus root 2. So that would be the most simplified version of that. Now, we can take these same formulas, these difference and sum formulas, and we can turn them around. Let's just see what that looks like. So evaluate. And basically here we will be given something that is already actually something from one of the formulas, and we just have to reconstruct backwards what it actually equaled. So let's go with something like this. Let's go with cosine 70 degrees cosine 20 degrees, minus sine 70 sine 20. Okay, so the key here is we have before us one of the known identities here, and we just have to figure out which one it is. And if we zoom in a little bit here, we can see that this fits precisely the pattern of the cosine addition formula. We have cosine cosine minus sine sine. Cosine cosine minus sine sine. So this is exactly right. And so we will proceed by just recognizing that this will equal cosine addition. So 70 plus 20. But 70 plus 20, I can do that. So this is really asking the cosine of 90 degrees, which is the x value, which would be 0. So that's how you turn these formulas around. You can recognize what has been given to you as being actually a something that came from one of these formulas. So you just look over the list of the formulas, find out which one it was, and then you can combine them to produce something like this. Another example might be something like the tangent of pi over 18 minus the tangent of 5 pi over 18 divided by, and then down here we're going to have 1 plus tangent pi over 18 tangent 5 pi over 18. Now, when we think about this, which formula does this fit? Well, it would appear to be the tangent subtraction formula that we've got here. So that's equal to the tangent of alpha minus beta. Oh, sorry. This was actually a mistake, a typo in my I misread my own example here from my other notes here. So this is supposed to be plus and minus, so that it matches the pattern of the tangent addition formula. In a lot of these, you can go either way, and it's fine, and it works out. But in this case, it would require us to know a tangent of an angle we don't actually know. So here, this was supposed to be a plus and a minus right there and there, making this the tangent sum formula. Tangent sum formula. So this is supposed to be a minus, that one's supposed to be a plus. Make a note of it. Okay. So then that makes this the tangent of, and now since they have the same denominator, I can just add the numerator. That's 6 pi over 18, which is equal to just tangent of pi over 3. Now pi over 3, that's the steeper one, and so that means a tangent out of the choices of root 3 versus root 3 over 3 would be just root 3. Alright, well that's all for section 6.5, in which we are just developing the most basic of the formulas. The next sections we will be covering will give us this box, this box, this box, and this box. These ones will be a subject for the next chapter. So that is 6.5. Alright, now for 6.6, what we're going to do is we're going to take the sum formulas and we are going to use them to spin out a couple of other categories of formulas, namely the double angle and the half angle formulas. So 6.6, the double angle and half angle. Formulas. So let's start with the double angle, which in this class is not going to be particularly useful on their own. They're going to be more useful in giving us the half angle formulas for us. However, in other contexts, these have a lot of use as well. So the double angle. So the key here is take the sum formulas and set alpha equal to beta. All right, what would that mean? Well, let's find our handy sheet of identities here and take a look. So for sine, if we zoom in, alpha and beta become the same thing. Then that means sine alpha cosine beta plus cosine alpha sine beta. Those would be two copies of the same term. And so what that means is that if we set them both equal to alpha, we have sine 2 alpha is equal to 2 sine alpha cosine alpha. How interesting. Now for the cosine. So remember it was cosine cosine minus sine sine. If alpha and beta are the same, that's going to be just cosine squared alpha minus sine squared alpha. Now, for the half angle formulas, what we're going to want to do is get versions of these that don't involve three different trigonometric expressions, cosine, cosine squared, and sine squared, but rather something that is a little bit simpler. And the way we'll find the simpler versions of this to use will be the Pythagorean identities. Which will allow us to replace cosine squared by 1 minus sine squared. And also, by the same token, sine squared can be replaced by 1 minus cosine squared. Okay. Well, what's that going to look like? If I first replace the cosine squared by 1 minus sine squared, that's going to be 1 minus 2 copies of sine squared. And if I do the other way, and replace instead the sine squared by 1 minus cosine squared, what's that going to be? It's going to be cosine minus 1 plus cosine squared, so that's going to be 2 cosine squared alpha minus 1. Okay, and then for the tangent, we just again take our formula. It's tangent plus tangent on the top, so it's going to be 2 tangent alpha, and then on the bottom 1 minus tangent tangent, so it's going to be tangent alpha squared, or tan squared alpha. Okay. Now, for the half angle formulas, the ones that we're going to actually make more use of than the double angle formulas in this course. But, like I said though, the double angle formulas, they have their uses in calculus especially. So, half angle. So the way this is going to work is we're going to take put little asterisks next to the 2. Take the ones with the asterisk above, solve for sine squared alpha or cosine squared alpha, whichever the case may be. Okay, so let's just do that and see where that takes us. So cosine 2 alpha equals 1 minus 2 sine squared alpha on the one hand. On the other hand, cosine 2 alpha is equal to 2 cosine squared alpha minus 1. Okay, now in this case I will add 2 sine squared alpha to both sides, subtract cosine 2 alpha. I will divide by 2. Alright, and then on the other hand, I can take this one over here and I will add 1 to both sides. I'm going to write the cosine squared on the left since that's the one I'm solving for. Add 1 to both sides. And then divide by 2. And usually this would be written with the 1 first, just so it matches the same pattern. Now, if I take the square root and I rewrite it with alpha over 2 for alpha, and then just alpha for 2 alpha. So I just cut all my angles and rewrite them, rescaled. Then what I would get is sine alpha over 2 is equal to plus or minus square root 1 minus cosine alpha over 2 cosine alpha over 2 is equal to plus or minus square root of 1 plus cosine alpha over 2. And then if I divide them, and simplify, it turns out I would get plus minus square root of, the top would be 1 minus cosine alpha, the bottom would be 1 plus cosine alpha. And for all of these, so use, and I'm just going to put this in a box here, because this is the punchline here, and use the quadrant of alpha over 2 to choose plus or minus. All right, and then it turns out actually that we can come up with a simpler version of the tangent formulas, one that doesn't involve the plus or the plus minus actually, and also that can be a little bit easier to use because it produces answers that won't require as much simplification. And the easier to use versions of the tangent will look like this. So the way that it would work is if we basically just take the result and multiply by the conjugate, that would give us one pathway there. Another pathway there is to use the yeah. So just we'll just do what I just said. So multiplying by the conjugate uh, will get us what we need here. So actually, here I'll just write it first, and then we'll prove it later. It's okay. Tangent alpha over 2 is equal to 1 minus cosine alpha over sine alpha, which is also the same as tangent of alpha over 2 equals sine alpha over 1 minus cosine alpha. Sorry, 1 plus cosine alpha. And, okay, so here's how I'll prove it. So, note from above, sine squared, 2 sine squared of alpha was equal to 1 minus cosine 2 alpha. From above. Also, if I have 2 sine alpha cosine alpha, that's the same as sine 2 alpha. All right, so now tangent of alpha is the same as sine alpha over cosine alpha, just by regular old definition. This is just like a side note that we'll use. So this is the definition of tangent, really. And now if I multiply the top and bottom each by sine, then I would get sine squared alpha over sine alpha cosine alpha. And then if I were to multiply the top and bottom of that each by 2 sine squared alpha over 2 sine alpha cosine alpha. And then if I were, sine squared, and so then if I substitute in those two things that I just noticed, it's 1 minus cosine 2 alpha over sine 2 alpha. And then here, if we rewrite alpha over 2 to become alpha and 2 alpha, sorry, I meant the other way. Alpha becomes alpha over 2, 2 alpha becomes alpha. Then we get tan alpha over 2 equals 1 minus cosine alpha over sine alpha. Now that's one of the two. It's the first one. To get the other one, we can then just multiply by a conjugate in classic 6.4 fashion. So then multiply by a conjugate. So if we have 1 minus cosine alpha over sine alpha, we multiply it by 1 plus cosine alpha over 1 plus cosine alpha. And then that's going to make a 1 minus cosine squared alpha, the difference of squares, all divided by sine alpha times 1 plus cosine alpha, which by the Pythagorean identity, that is just the same as sine squared alpha on the top. So we have sine squared alpha on the top, sine alpha, 1 plus cosine alpha on the bottom. Those will cancel, and that'll give us just a lone sine alpha on the top and a 1 plus a cosine alpha on the bottom. So that gives us the other of the two. All right, now to use these, using these formulas. Treat the given angle as alpha over 2. Find alpha, then use the correct equation. Simplify by multiplying by the conjugate where appropriate. All right, let's give this a try. All right, so let's try to find, for example, so find and simplify. Try to find the sine of 22.5 degrees. So this is going to be our alpha over 2, which means then that alpha, we would multiply both sides by 2, and we'd get alpha equals 45 degrees. Nice. 45 degrees. That's a well-known angle to us. So then, how do we proceed from here? We just have to think about what the formula is for sine. Also, this angle is in quadrant 1, which means that the answer is going to be positive. So sine 22.5 degrees is equal to plus or minus, and I already know it's going to be plus, square root of And now here what we're going to have is 1 minus cosine 45 degrees over 2. And so then that's equal to positive, and then 1 minus root 2 over 2 over 2. And then what we'll want to do here is multiply the entire top and the entire bottom by 2 inside the square root. So it's 2 minus root 2 over 4. And then that actually simplifies a little bit. Square root of 2 minus root 2 divided by square root of 4, which then we can evaluate. Square root of 2 minus root 2 all divided by 2. So that's the most simplified version of that we can come up with. Now it was, so what we had to do was multiply by any kind of fraction that we needed to, and then we dealt with the square roots and such the way we will typically have to. Alright, let's try another one. This one, let's go with some radians. Tangent of 7 pi over 8. Now, 7 pi over 8. So this is not convenient because for one thing it's in radians. So let's think about what we can do here. So pi over 8, so that is, so that's going to be the same as the 22.5 degrees, and then this will be 7 times that, and so that's going to be 45, 90, 135. So this is going to be, or here actually, the easiest thing would be just to use a calculator here. So 7 pi divided by 8 times, and then 180 divided by pi. 157.5, so good. So alpha over 2 is the same as 157.5 degrees. Okay, so be it. And then that means that alpha itself is equal to that times 2, which is 315 degrees. Alright, so first off, 157, that is quadrant 2. So tangent will be negative there, if that's of interest to us. So if we're using the square root formula, that would be important to know. If we are not using the square root formula, then it's not as important. And 315, by the way, is just 45 degrees over here. Okay, so if I want to use one of the other formulas for tangent, I can just look them up here and decide which one I want. Not really much to decide between the two of them, but in general, the easier one will be the one to deal with will be the one that has just one term in its denominator. So then, this is equal to, and I'll go with the one. So I'll go with the one that has just the sign on the bottom. 1 minus cosine 315 degrees, all divided by sine 315 degrees. It's going to be 1 minus, and then the cosine of 315 degrees is going to be root 2 over 2, divided by sine of 315 degrees, which would be negative root 2 over 2. And here I will rationalize the denominator and I will multiply everything by 2. Actually, perhaps the easiest way of going about this would be to rewrite this fraction as multiplication by the reciprocal. In either case, whatever I'm going to do here, I will start by multiplying by 2 to get rid of those little fractions. 2 minus root 2, all divided by negative root 2. If I multiply the whole top and whole bottom by root 2 over root 2, then what I'm going to get now is going to be 2 root 2 minus 2, all divided by negative 2, which will cancel mostly, and will give us 1 minus root 2 as our final answer. And just in general, these are the sorts of calculations that we end up producing as we go through these. Alright, well, if you can do a couple, and if you can do the tangent ones, you can do anything. For the tangent, if I were using the formula that involved the plus or minus, I would use the quadrant to determine that. If, however, I am using the formula that does not involve the plus minus, then I just have to strategically decide which one I'd rather have be in the denominator, and usually it will be the one that will have only one term, so that you don't have to go through as much to rationalize the denominator as you otherwise would. So that's how that would have to go for a tangent. And to do any of the others, you just use the appropriate formula. You just have to know what to plug in. You make alpha over 2 your given angle. That's the important thing. And for the final installment of this lesson, we have one more category of formulas, and these are what are called the product to sum and the sum to product formulas. Alright, so the idea here the sum and difference formulas can be combined in different ways to produce specific terms that contain particular products of sine and cosine. The resulting formulas are called the product to sum formulas, and definitely they need not be memorized. So very few people use these on a regular enough basis to make memorizing them very productive. However, you should remember that they exist, that these are a thing, and that and so that if you ever need them, if you remember what they're called, you can look them up. All right, so let's look at what these each are. So the particular combinations that we're talking about would be sine alpha, sine beta, and then cosine alpha, cosine beta, and then finally sine alpha, cosine beta. All right, so these are the intended products. Now, if we look at what it says here, we can take the difference in the sum identities and they can be combined in such a way as to produce these particular outcomes. So let's look at this. Let's say we wanted to make the sine sine. So the sine sine. How do you get that? So if you look at the cosine addition and difference formulas, those each have a term sine alpha, sine beta. So if I were to take the positive one here and I were to subtract this one, then the cosines would disappear and I would just have two copies of sine sine. And so then I would just divide it by 2 and that would produce the product to sum formula 1/2 cosine alpha minus beta minus cosine alpha plus beta. Now for the cosine cosine, I'd take the same 2 here, and instead of subtracting them, I can just add them together. So then the sines will disappear, and the cosines will survive. But there'll be 2 copies, so I'll divide by 2. So that's how I will produce the cosine cosine formula. And then for the sine cosine, I look at these two, and I see that if I were to just add them together, then the cosine sine terms would disappear and the sine cosine terms would survive. And so those are the combinations that would produce each of these. So now, if I put that into practice, I'd have 1/2, and remember what this one was I took the cosine difference. So cosine of alpha minus beta, and I subtract the cosine sum, and I do 1/2 of all of that. Now for this one, for cosine cosine, very similar. Just instead of having to add them or subtract them, I add them. Oops. So I'll write it in the same order that I wrote this one. It doesn't matter which order we write them in, but it's written on your formula sheet in this order. So I'll stay consistent with that. And then for the sine, it was, if you remember, we take the sine addition and we just add on the sine difference. And that will double the copy of terms we want and cancel the ones we don't want. And so that will produce, and so then we do 1/2 and that produces that. Now, if we want to turn these around a little bit, we can do so in order to produce a different version of the same types of formulas called the sum to product. The sum to product formulas are the result of rearranging these equations and changing the variables. So in particular, instead of regular old alpha, we change that to be alpha plus beta over 2, so the average of them. And beta becomes alpha minus beta over 2. And then what happens is when you then subtract them, that produces just beta, or sorry, add them, that produces just beta, and subtract them, that produces just alpha. And through a bunch of manipulation, we get the sum to product formulas. And those have these forms. So sine alpha plus sine beta is equal to 2 sine alpha plus beta over 2 cosine alpha minus beta over 2 sine alpha minus sine beta, on the other hand, would be very similar, except that it would be 2 sine alpha plus beta over 2. Sorry, this one is minus. And cosine alpha plus beta over 2 cosine alpha plus cosine beta. This is equal to 2 cosine alpha plus beta over 2, and then cosine alpha minus beta. And then finally, cosine minus cosine. That's negative 2 sine alpha plus beta over 2 sine alpha minus beta over 2. And again, the details of these are not important to exactly follow in every case. It just comes from creative rearrangement of the equations and redefinitions of the variables. So these also do not need to be memorized. These also need not be memorized. Very few people know these off the top of their heads. But here's the important thing. So using these. So essentially, you just have to define the alpha and your beta to match what's given in the problem, and then hope for the best. So define your alpha and beta. The angles in the problem, and then simplify according to the formulas. Alright, so let's just try something like this. So the way these kinds of problems look is like this. So we have maybe cosine 285 degrees times cosine of 195 degrees. Alright, well, here we're just going to take alpha equals 285, beta equals 195, and we have a product, so we're going to use the product to sum identity that involves cosine, cosine. And so then that means alpha minus beta, we're going to need that, and alpha plus beta, we're going to need that. So alpha minus beta, it turns out, it looks like it equals 90 degrees. Good to know. Alpha plus beta. So if we were to add these together, we're going to get, is it 300? 380? I mean, 500, 580. What am I doing? No sense being proud after at this point in the video. So let's just not be foolish here. 285 plus 195. 480. 480. That's right. That makes more sense. It's gonna say 480. 580 didn't strike me as a very familiar number, but this one is much better, and that's, for the record, 360 plus 120. Good to know. And just, again, don't take any leaps here. Yep, that was 90. Okay, well then, I've got all the ingredients I need here, and I just have to put them into practice here. So cosine alpha cosine beta, so cosine 285, cosine 195 is equal to 1/2. And then here, the cosine, remember that came from adding the cosine difference formula. And the cosine addition formula. And then that equals just 1/2 cosine 90 degrees plus cosine of 480 and so that's going to be 1/2 of 0 plus 480 is over here, so it's going to be negative 1/2, and so the result will be negative 1/4. So that's how we would use one of the product to sum formulas. And now let's see how we would use one of the sum to product formulas. So let's say we had something like this. Sine 255 degrees minus sine of 15 degrees. Now notice, by the way, we could actually technically evaluate this by breaking it into two parts and using the sine addition or subtraction formulas, but that's actually exactly what these are all based on. So now we just look over the list of the sum to product formulas, and we find the one that matches this. So sine minus sine. So there it is. All right, so alpha is 255. Beta is 15. And then you just look at the formula. You don't have to try to be a hero here and memorize it. And so it's 1/2, and then the formula was 2, oops, wrong category of formula. So it's 2 sine alpha minus beta over 2. So that's going to be 255 minus 15 over 2. And then cosine 255 plus 15 over 2, which is then going to equal, so it's 2 times sine of, alright, what's that going to be? 240 divided by 2 is going to be 120. And then the other one is going to be 270 divided by 2 is going to be 135. And then we just would figure out where these each are. So 120, 135, and we know what each of these are. So the sine is going to be root 3 over 2. Root 3 over 2, and the cosine here is going to be negative root 2 over 2. And so what do we have all together? One of the 2's will cancel, and we're going to have negative root 6 over 2. So that's how we would use these if we had specific angles given to us. And then the last category is where we are rewriting expressions in theta. So the last category of problems would be something like this, where we have, so express as a sum. And here we might have something like sine 3 theta. Sorry, I lost my place here. Sorry, we'll have sine 3 theta, 5 theta. So sine 3 theta, sine 5 theta. Okay, well this looks a little different, but really it isn't. And the way we will go about it is we just take what we're given and we just do the same thing with it as we would do ordinarily. So 3 theta equals alpha, 5 theta equals beta. Then sine alpha, sine beta, that is just one of the formulas, and it's going to be 1/2 times cosine alpha minus beta minus cosine alpha plus beta. So we just think about what this is going to be. This is going to be just equal to 1/2, and it's going to be a cosine of negative, so 3 theta minus 5 theta is negative 2 theta. And when we add them, it's going to be cosine of 8 theta. And so that's equal to, and here technically, since cosine is even, this can go away. I'm just going to have 1/2 cosine 2 theta minus 1/2 cosine 8 theta. So there it is as a sum of, or in this case actually technically a difference, close enough. And then the other way would be we are given something that matches the sum to product rule. So maybe we have something like this. So rewrite as a product. And the equation, or the expression that we might have, would be something like, let's say, cosine theta plus cosine 3 theta. Well, once again, we just have our alpha equals theta, our beta equals 3 theta. And you just find the appropriate formula. It is cosine plus cosine. So that's going to be cosine alpha plus cosine beta equals 2 cosine alpha plus beta over 2 cosine alpha minus beta over 2. Which is equal to 2 times cosine of theta plus 3 theta over 2. Cosine of theta minus 3 theta over 2 is equal to 2 cosine, and then here we have 4 theta divided by 2 is 2 theta, and cosine, we have negative 2 theta over 2 is negative theta, and so again cosine is even. So we have 2 cosine 2 theta cosine theta. So now it is a product instead of a sum. And that's how you use these formulas. We will not be expecting you to memorize these. The sheet that contains all of these, as well as some other formulas, can be found on the D2L site for this class under Content. Okay. Well, that'll do it for this episode of Math 112. Thank you for joining me, and I'll see you next time. Bye.